So let's get started. So today my talk is about OpenR. OpenR is the routing protocol we built at Facebook. I'll try to go over design more than code, although this was mostly software work. But just to give an impression, how many people here actually write code often? Right, quite a few. Okay, that's good. So for those of you with more details on the coding side, but let's get started. So this whole story about, hey, let's create an routing protocol. Brian, give me a weird sign saying something on my microphone. Anyways, so we've been talking about our routing protocol for years. As Brian mentioned, BGP became kind of a standard in data center to some extent. I won't say standard, but in the big data centers, people often use that for various reasons. But after a while it gets boring. So we spend a lot of time definitely working with goddamn RFC. It can take 4 years actually to get to standard. It was mostly formalities. If you're at ITF, there's lots of small details you have to go through. People give us some weird feedback, change this word to this or something like that. I think this was submitted in 2012. We only approved it last year. But now basically we do have a solution, and BGP works fine. And unless your vendor screws up pretty badly, right? Everyone pretty much has it working. So the idea was BGP was great, but people, especially at Facebook, like to experiment. They like to do stuff, change things, especially in the network. BGP has some limitations. If you think about this in the fabric, in the networks, sometimes you have issues like load balancing. You want to control routes specifically, do more precise routing, manipulations. This wasn't possible with BGP. It's not a big deal, but at some time we realized, hey, we want something better. And experimentation is a kind of part of a culture at Facebook. People like to do things to see what they can do, just to have an option to do something different in the future. And so we spent some time, I think, ever since I joined, discussing the options for routing protocol. And nobody likes this protocols, apparently. People like link state. ISIS is kind of reference that everyone likes. Because ISS, if you ever looked at documentation, is kind of written in this boring British language, but extremely well documented. And the architecture of the protocol was really, really nice. And so we use this as reference. But then we said, okay, just trying to build our own routing is kind of boring because it's already a solved problem. I mean, ISS works, OSPF works, BGP works. The only problem with these guys, with protocols, is if you try doing your own, you'll probably screw up very quickly because it's hard to write a good protocol from scratch. So anyways, we said, okay, what we want to do is something bigger than routing protocol. It's a system that exists in the network and allows us to build applications using message bus. So message bus is a concept very well known in the industry. Lots of implementations with ActiveMQ, RabbitMQ, all these implementations that have message brokers and so on and so forth. But we wanted something specifically for the network. So the next one was, if you ever look at the Zebra or Quagga routing suites, they're written in C. It's kind of 90s old school style. It's nice, I mean, if you like C, but it's not very, I'll say, not very high level, should put this the right way. If you want to build something faster and easier, you can use modern libraries and techniques and build something in much more compact way in the code. And to be honest with you, I think the initial thing we did when I joined, we wrote BGP in Python, which is very fast but very slow at the same time. And so the idea was, once we have this great message bus, we can build a routing as a single application on top of this. All right, so at the same time, I think this was 2015, we began working on Terragraph. So anyone heard about Terragraph in the audience? So, well, Terragraph is a Facebook's project. It's a kind of wireless mesh network, 60 gigahertz, high speed. The idea is to build an alternative to fiber technologies to be able to build high-speed internet in some in the areas in the cities, for example, we don't have fiber. And so these folks came to us and say, hey, it would be nice to have some routing solution for us, something we can tweak fast and easy. And so this is how kind of it became material. OpenR became, first application of OpenR became Terragraph, or vice versa. Okay, so let's go over the design. So how does OpenR look like, how does it work, and so on. So first of all, 0MQ. 0MQ, as I mentioned, we need some message bus, right, to exchange data between the routers. If you remember, like in BGP, you have TCP connections, it's all great, but if you look at protocol spec, in OSPF or ISIS, most of the text is spent around defining formats and the handshakes and other crap, sorry, not crap, just other stuff to make things work, right? It's super painful to do it on your own if you do it personally, but if you take some open source stuff, like OpenZMQ was our choice, you kind of avoid all this tedious hassle of having to implement these low-level details. So it saves a lot of time and testing as well. Because ZMQ is a well-known kind of open source library, works really well. It allows you to create very nice configurations and so on and so forth. The API is also really nice. If you use ZMQ, it has really nice socket-looking API. It's really easy to use. There are some caveats there, I'll be honest with you. Like ZMQ has some knobs you don't know about, which you may kind of forget about. It can pretty much get you badly. But overall, ZMQ has been proven to be very robust and well working for us. So this is just an example, like message patterns in ZMQ. So ZMQ allows you to build these arbitrary topologies of messaging agents. You can pass messages like in a tree fashion, in a mesh fashion. For us, I would say probably most important one was publisher subscriber. Because if you remember, like for instance, in OSPF, ISIS, lots of time is spent on flooding, right? You receive message, you send it to your neighbors. This mechanism, if you do it on your own, is kind of not so nice. If you delegate this to a library, it's super simple. It's like basically like two functions. The other thing was Thrift. So Thrift, it's a format for message encoding. It's also a library for remote passenger calls, RPC. So pretty much in Thrift, you can define interface for a server, message formats, and generate you all the code to do these functions. It's kind of a shortcut to avoid writing lots of like server code and client code. For us, the most important part was encoding. So Thrift allows you to define these really nice looking structures, like simple language, IDL. Say this one defines adjacency, like OSPF, or like in our case, OpenR adjacency. You can see all these nice types, string, IP address, IP prefix, tralala, it's all great. And you don't have to write all the parsing code on your own. The great part is that you describe the structure and you get the code for free. It's all verified, it's all generated, you don't have to spend time on low-level details. And so together combined, 0MQ and Thrift gave us this message bus for our OpenR. So this is the foundation, the transport. If you may think about this like a BGP message, like TCP and BGP message format for our OpenR. But instead, we use Thrift in our 0MQ. So this is the main gray diagram for OpenR. If you ever looked at ISIS documentation in the past, this looks very familiar. Like in this big square, you can see 4 components. This is the main pieces of OpenR. So there's decision component, there's a key value store, link monitor, and a fib, the component responsible for programming the forwarding tables. On the right side is like just 2 components of the same type from different router, just to show how we communicate. So if we build all the communication patterns, this is how it looks like. This is message flow. So we do form peering sessions, just like BGP does, between the key value stores. And so these peering sessions are done using 0MQ. We also send special hello packets between the link monitors to discover neighbors dynamically. So this is in ZMQ. As you'll see later, this is based on a UDP. But inside this big box, you can see this very simple, almost circular flow of messages. So link monitor talks to key value store talks to decision, and so on and so forth. We're going to walk over all these components in more details, so I'll skip the details for now. Okay, so key value store was the first component written for OpenR, and pretty much they say like at Facebook everyone has to write key value store. It's like almost a tradition. because key value stores have the simplest possible database format. So key value store is a process but runs on every node in the network, right? You may think about this as something very close resembling LSDP in OSPF, right? OSP database in ISIS, except that it can store any data, not just linked adjacencies, not just routing information, but any information. So key value stores talk to each other using ZeroMQ. They synchronize the states, and they exchange with contents in the network. So you may think about these key value stores as having the same content in the network. So eventually, we will all exchange the data with each other and synchronize the content. The most important part is that the values in this key value store are Thrift objects. So it's not like just structureless binary blobs. They have structure, which we describe using this nice, clean IDL. So when you receive these key value objects, you don't have to spend time parsing them. You already have a code to do it for you. So if you remember, like in OSPF and ISIS, they spent some time trying to optimize the flooding. So flood optimization was kind of a problem, maybe slightly exaggerated sometimes, maybe not. But the problem was if you have always meshes and you do message flooding, it's not very efficient, right? So look at this mesh on this diagram. There's definitely some inefficiencies, right? You may flood messages twice sometimes. So we did some work just for fun. I wouldn't say it was super necessary because performance was fine to optimize the flooding. So first of all, when you have this mesh, you can participate in clusters. So clusters are very similar to BGP ASNs, right? They group the nodes, except there is no administrative domains. They just define the boundaries, flooding boundaries. This could be arbitrary. In this case, this could be also automatic, but let's say for simplicity, you define these clusters by hand. Then inside each cluster, you can prune the duplicate links. For this to happen, you just run spanning tree algorithm. You can run spanning tree algorithm using this hello protocol, compute the duplicate paths, and prune them. So which already means you can send messages only over the spanning tree. So in some sense, you get a spanning tree inside the protocol, and then this saves you on message flooding. So this kind of optimizes flooding inside the cluster, of course at the expense of longer stretches, because now if you have a message coming from one node to another, it has to go along the tree. Between the clusters, we use this classical BGP trick. You can do path tracing. As you send messages between the clusters, you trace a path, it comes back, you drop it, if it has the same AS number. Well, in our case, it was just cluster number. So like this message comes around, comes back, and gets dropped, because in path tracing, you have your own cluster number. And similarly, like a longer flight, cluster C message comes back cluster C and gets discarded because of path tracing. So there's essentially two mechanisms to optimize flooding, intercluster and intracluster. They're very straightforward. As I mentioned, it's not like we're super necessary. We only see use cases in the very dense meshes. You have say 10,000 nodes, and some portions are very dense. Kind of then this helps. In most cases, you can just flood obliviously. Okay, so this was the key value store. The second piece is discover your neighbors. So every protocol has some sort of hello messaging, right? In our case, we didn't go fancy. We built a separate module. Its sole purpose is to send hello packets and discover neighbors. We use just UDP packets. There is no special protocol like OSPF has, or EIGRP or whoever. Just UDP packets sent to multicast address. Inside every packet, we have a Thrift object, which describes, oh, this is me. I think called the Spark, protocol called Spark. Every message describes yourself and neighbors you've seen. So very, very similar to OSPF has, right? Except that encoding is now nice and clean. You don't have to have this weird binary parsing like OSPF had before only, right? For example, fields, right? It was very painful. But you can see here, this is the whole definition of protocol, just 3 structs. And I think it didn't change in 2 years. The nice part here, you have neighbors you have seen, you have signature. So from day one, with authentication and encryption of hello packets. By the way, encryption is pretty expensive, so sometimes you have to turn it off. If you have lots of neighbors in the data center, say a few hundreds, and you try to encrypt every hello packet, your CPU spikes a lot. especially on some lower-end boxes. Hello pretty much does two functions: discover neighbors and test bidirectional condition. So you want to make sure that neighbors hear you. And to be actually, I think, initial implementation, but to roll like 3 years ago, we just had BFD. But BFD was kind of old school, and we built something simpler because Spark is even simpler than BFD in terms of state machines. Okay, so next is link state tracking. So hello protocol tells you, okay, this is my neighbors, this is my adjacencies, but how would you communicate this to the others? So link monitor does this hello message sending, right? Once it discovers neighbors, it talks to Kiwi store. It says, okay, hey, this is my neighbors, they're bidirectional, I know about them. And so this publishes and propagates everywhere. So notice that, quite interestingly, hello packets and these neighboring connections are independent. We pretty much have like, say, 10 neighbors, but it can only peer to one of them to like do like mesh reduction. So like unlike in OSPF, you have like hello packets pretty much aligned with the adjacencies. And so key value store does connect to neighbors based on hello data. So when you discover somebody, and if you go, okay, this router is worth peering to, you tell key value store, okay, shoot the session, start the connection, and form a ZMQ association. And then link monitor, aside from talking to key value store, also talk to fib. My trick here is that we want to have like fast fault detection. In this case, you really want the link monitor to talk fast to fib database, to tell the fib, okay, this interface is down, remove all routes which are using this interface. So we'll talk about this a little bit later in the other slide. Okay, so decision module, surprisingly, is the simplest one. So if you think about OSPF, this is where your SPF is, computations. In our case, we, I think, simply took some open source library, I think it was Boost graph library. You give it information from key value store, right? Like prefixes and topology data. You build the graph, you compute the shortest paths, and you push them down to a fib. It's very straightforward. It's really clean, nice to test, because you can feed the data to this module, test it. What's interesting is that decision computes kind of, in our implementation, does full snapshot, full computation. So remember, like, there was lots of work in ISPF, incremental SPF, in the past. Comes out, CPUs we have now pretty powerful. In most cases, you can handle like full snapshot computation like very easily. I mean, we've seen troubles in some low-end platforms, but like even in Terragraph, you have ARM CPUs, for example, which are pretty powerful and can handle all this stuff easily. We'll discuss later, like decision does slightly more than SPF, but in its basics, it just computes shortest paths. So the nice part, you can replace this module with anything you want. You can compute something more fancy, like TA tunnels if you want, for example. But we didn't need this for our projects. So this is just messages that decision uses. This is the data it consumes from the key value store. I'll just use this for an example. So you can see it's like only like 1, 2, 3, 6 messages, and this is your whole protocol to talk to key value store and get the data. So once again, super nice and easy, right? You don't have to spend time trying to optimize this encoding formats like you did in OSPF. Okay, LFAs. I mean, loop-free multipath was a very hot topic, I think, 2005, 2006, when people say, hey, FR is great, but we want something for IP. And the idea is very simple. If you have ECMP or equal cost paths, it's all great, right? You pick up 2 paths, they're amazing, you all share. I mean, there's some downsides to ECMP. Like debugging ECMP is sometimes painful because you don't know which path you're taking sometimes. But in most cases, people like ECMP. The more tricky part is non-ECMP paths, right? The path detour down is longer than the other paths. However, the condition is that it's actually loop-free. So if you send your packets to a node down there, even though it's not shortest path, it's not equal cost multipath, you'll see the loop-free. And so in our case, decision finds all these loop-free alternatives and may install them in addition to the ECMP. So by default, we don't do that because it's really hard to load share across all these weird paths. And initially, we even have routing loops in the first implementation. we only keep this LFA, the backup paths, in the fib for protection, path protection. And as you know, LFA has this one, I would say, caveat weakness. We don't guarantee you full coverage, right? You need to have some tunnels like remote LFAs to cover everything. So for now, we do have this optimistic, like opportunistic protection for most cases, but not for every possible scenario. All right, data plane. So this fib module, I mean, it sounds confusing, right? It's not actual for database. It's the special software component that computes the routes, prefixes, and next hops. So the decision has the graph topology, and the fib, it has the actual like forward information to push down. It subscribes to information decision, so it receives all these full snapshots of the routing data, and then talks to the low-level SDK. And in a sense, this is the only component that has to talk to the low-level components of the hardware. So for example, on FBOSS switches, it talks to Broadcom SDK, right? On Terragraph, there's another SDK to talk to the SoC to program the fibs. But all this data is encapsulated, sorry, all this SDK is encapsulated in this one module. So everything else could be run on any platform. Only the fib has to be ported to specific hardware. As I mentioned, LFAs, right? LFAs have been pushed down by decision to the fib, and so fib knows, okay, this is my active paths, and this is my backup one. And so when a link monitor tells me, hey, there's a link going down, the fib can switch immediately to the protected path. So it's not like it's super fast. In most cases, I would say it's less than 50 milliseconds, but unfortunately, it's bound by CPU, right? By a CPU, because you can't do this in hardware on every platform. So we have to do this in software. So when you have a path flip, you have to push the new path down to the hardware, and with the slight delay, it depends on SDK how fast you can update the hardware. Like this is like a notorious known problem on the big platforms, like large chassis boxes. If you have to push fib update to the line cards, it may take some time because always RPC communications. In our cases, most of the platforms we have, they're kind of localized. There's always complex communication patterns. So we've seen recovery times less than like 50 milliseconds in most cases, unless your CPU is super busy. If your CPU is super busy, you definitely have to wait longer. Okay, a few other things. IPv6. So IPv6 is a big deal for Facebook. Everything inside Facebook is IPv6 now. I would say 99% of traffic is IPv6, of course inside, not outside. And so OpenR was initially built using v6 only for communications. For instance, one thing is transport, right? All these sessions you form in ZMQ, they use local addressing. So it's only link local. You can bootstrap OpenR without any addressing. So you can drop on the box, you auto-configure IPv6. By default, it's auto-configured. You discover neighbors, and all these sessions you form by using link local addressing. You may pretty much just run this without any configuration. Of course, if you have to route something, you will have to announce this in OpenR. But to bring this up, you don't have to put like neighbor statements or anything. You just have to have a proper authentication keys. V4, of course, we had to handle IPv4, right? People didn't like the idea of being v6 only. But it's very simple. You just carry v4, assume it's the same topology as v6. And you forward v4 packets using the encap information from v6 packets. So you don't have to have v4 addressing on the transit links. You simply use, okay, this is my MAC address, just rewrite within this MAC. You can transport v4 packets using the v6 topology. Well, which means, of course, the limitation, they have to be congruent in some sense. Terragraph, right? I mentioned Terragraph briefly before. So Terragraph, it's an interesting case because it's a very big, large mesh. When you deploy Terragraph, it gets kind of a grid on the city map. You run this along the lines, the power poles, the light poles, and so it forms this one complex mesh. The nice part of this mesh is lots of backup paths, so you can have always detour paths available for you. The complex part is pretty dense, so you have very large topology. Per design, Terragraph can scale up to like 10,000 nodes. So far, I think we have deployment in San Jose. It's not that large. I think it's only a few hundred nodes, but we eventually plan to grow this over like thousands of nodes. And OpenR, in this case, provides basic connectivity, like routing and fault recovery. We also have a central controller. So this is kind of specific for Terragraph. There's a central controller that talks to every node and provides more like smart, intelligent decisions. The idea was we were going to have traffic engineering and push this path centrally from a controller. But OpenR still provides these very basic fundamental pieces of communication and routing. So address allocation was the other thing. Once you have key value store, you can kind of do, I don't know, kind of an ARP or with key value store. You can allocate yourself addresses on every node. So the way we do this in Terragraph, we have like one seed prefix, let's say /48 IPv6 for the network. You inject this in key value store, and then every node can sub-allocate the addresses from there. There's actually, I think, an RFC in IETF for HomeNet area, where we have a similar technique. And this message allows you to auto-configure addresses of a network with zero configuration. We call it zero conf, but zero conf is different technology. But this was kind of a nice thing for us because we kind of saved time on this whole IP addressing pains. And itself, it just uses key value store. And the nice part, you can allocate anything, not just addresses. You can allocate some other resources if you need. Okay, Terragraph was the first implementation. So we definitely do right now experiment in data center with OpenR. It's more sensitive area because people are, hey, you know, there's live traffic, you know, let's be careful there. Right now, we mostly use in passive mode to discover topology and test routing decisions against BGP. But the actual use case is Express Backbone. I think there was a talk 2 weeks ago at Scale, Networking at Scale event about Express Backbone. Express Backbone is our own private backbone built on like commodity boxes using OpenR and a central controller. And in this case, OpenR runs, I think, like on a few tens of boxes, providing this routing functionality, address allocation, and a few other things. And this is actual live traffic, and it works pretty well. I think we've been using this for over a year now. As I mentioned, like one of the key traits you can see is OpenR being collocated or integrated with central controller. So there's like distributed intelligence for like fault detection and rerouting or configuration, and a centralized programming for more complex logic, such as traffic engineering. And central controller isn't OpenR, it's a different system. But in most cases, this combination, this hybrid of distributed centralized was very efficient for us. Okay, almost on time, perfect. Just to recap, the key motivation for us just to start OpenR was to be able to kind of control our own destiny, right? If you have been in conversation with vendors about changing routing protocols, you know it may take a while to get a new feature. And once you have your own thing on hands, you get different set of problems, of course. You now own your own destiny, your own bugs, your own issues. It's more fun, it's also more kind of stress, but we prefer it this way. The other kind of insight for us was building a platform for applications and not just a routing protocol. Because I mean, routing is a solved problem, more or less, in most cases, but once you have the platform for applications, you can do much more in the network. And probably the last lesson learned is this hybrid of centralized and distributed works really well. You can do lots of super smart stuff in distributed fashion, but you can definitely delegate with central controller. And vice versa, you cannot centrally control faults and rerouting the network, but you can definitely do this more efficiently in distributed fashion. And I think that's it. Thank you so much. Ready to take your questions. Of course, yeah.
And adjacency information. So is the adjacency information like propagated through the whole network?
Yes. You can think about this pretty much like OSPF or ISIS as a single area. We didn't actually do multi-area because it worked really well, even with 10,000 nodes and now testing, single area worked just fine. Even for like, I think we tried, oh my God, 10,000 nodes, maybe 60,000 links was working pretty reliably.
So what's the difference between this new code you build in comparison to OSPF?
Oh yeah, so as I mentioned, routing-wise is very similar. I would say it's probably simpler because you don't have to implement lots of low-level details. Like first idea was, if we try to do something from scratch, should we try to re-implement or build something more like more abstract? And more abstract was with key value store and data bus, and then routing was just a simple function on top of this. Because functionally, it's very similar to like OSPF single area with LFAs and a few other fancy things, right? But the next part, just to give you an example, to build the LFAs, it took us probably like less than 1 day, right, of code. Probably like this much of code to do LFA check. And if you remember how long it took to roll LFA in major platforms, it probably took a few years to standardize and deploy this. And it's more about the speed of changes, right? Not just like about doing something like very creative.
Oh,
Mm-hmm.
thank you.
Thank you.
So you actually answered my question. I was going to ask about multi-area and if you guys did anything with it. So you answered that. I'll ask another question then. I was wondering, how do you guys solve a problem with multi-point networks, like similar to how OSPF and ISDIS would use the DR or DIS if, say, you had 100 routers or whatever on one Ethernet segment? Is there something similar that you're doing with OpenR?
Right, so first of all, OpenR was built initially for only point-to-point networks, just point-to-point. If you look at broadcast segment, you'll see it like this full mesh of connections. And in our case, in most cases, we never seen large broadcast domains. It's only like maybe 4 or 5 boxes max. The only time, I mean, even data center, it's all point-to-points, right? There is one use case we have right now. We can actually have like maybe 30 boxes, and like with we'll just simply do the same stuff what OSPF does, or actually ISIS. You elect one DIS, and you only connect to this guy. You still send hello packets to everybody, but you only form adjacency to this one neighbor. And if this neighbor dies, you switch over to another guy, right? So just very simple, traditional file induction. Like all this probably been solved like in 70s, 80s. People kind of figure them out. It's not like you can do something more original. You can just try to make it more simple. Probably that's it.
Cool, thanks. Thanks for the great presentation.
No, thank you. There's a question there.
Hi, Yasser from DePaul University. Thanks for the great presentation. So my question is, how do you guarantee the security of OpenR? What protocols are you using?
So luckily for us, this was ZMQ. ZMQ has methods for data encryption and authentication. They took it from, oh my God, what was this called? Dave Bernstein's. So basically, as a protocol, is like elliptic curves only. So you use private key crypto to sign and encrypt packets. It's elliptic curves. It's kind of CPU intense, but we use this for authentication and packet encryption. So if you mentioned, like, if you notice hello packet has a signature. So in every hello packet, you send your public key and a signature to authenticate yourself. Right now, every node, when you bootstrap, we give them list of keys which they can accept. There's actually 2 modes. If you're curious, one mode, you give them static list of the keys of the neighbors they can expect, or you put a node in learning mode. Just like in SSH, in secure shell, you can learn the keys from the neighbors and freeze them in the memory when you don't accept any other keys. So this is called learning mode. When you bootstrap a network, you say, okay, learn all the neighbors, remember the keys, and then switch to a freezing mode. Just these 2 things, and all the crypto authentication is just public private key authentication.
Right, question? Can you hear me okay?
Yep.
John Christoph from DePaul. It seems mostly like a replacement for OSPF and ISIS. Is there any thought, you didn't mention the word policy, and I wonder if there's any capabilities to do any of that sort of stuff here.
Right, as I mentioned, like always kind of smart routing decisions are delegated to central controller. Like in Express Backbone, we do segment routing. And segment routes are computed by central controller. Like on ingress nodes, you have policy rules which say, okay, match this prefix and this DHCP and apply this label stack, right? But all this intelligence is, all these kind of smart functions are pushed to central controller. Because it's really hard to do this. If you remember like out of bandwidth, it's very painful to debug and kind of analyze. It sounds great to do it distributed, but it doesn't work really well. There are some things that work better centralized. And like more with smart things, we just do them there in central controllers. All right, I think that's it. Thank you very much. Right.